Good afternoon, everyone. Welcome. Hope you're doing well. Let's see. We are on chapter 5. We started that just a little bit last time. We're talking about solutions, right? So if chemists have something, they have solutions. Get it? Anyway, my little joke for the day. Doesn't work very well on Zoom. I think I'm the only one laughing. Okay, let's see. Questions. Do you have any questions on anything before we get started today? Again, remember, take advantage of the TAs, get some help on problem sets, office hours, get help, ask questions. You know, we're right about halfway to the next exam, so that'll be coming up before you know it. I'm watching you on mastering, and I see that most of you are keeping up pretty well, but a few of you are falling behind. So make sure you catch up quickly, okay? You don't want to fall behind. In this class, it's the death knell, right? Hard to catch up. Any questions or comments before we get going here? Use the raise hand function on Zoom. Yep. Alexander.
Yeah, I'm just noticing that, so even though I figured out how to change my name on the Zoom thing, I don't know how to keep it the way I want it to be. Is there a way to do that?
Oh gosh, does anybody know? I think under your profile maybe?
You could click on it. Try clicking.
I mean, I can change it right now, but to like next time we meet, it'll probably be back the way it was.
I think you have to stay logged in, or you have to like log in each time. Like if you click the link, it just adds you on, but it doesn't log you into Zoom.
Taylor.
Yeah, hold on. You can go, so you see the little sidebar with everyone on it?
Yeah.
Okay, so you put your mouse on there. You see a little blue 3 dots, a little blue box like that with 3 dots in it.
Oh.
You see that? Like on your profile, on your video.
Wait, so go to the participants, right?
No. So like the sidebar with everyone's faces, like with Tro and...
Oh, I see. Okay.
Yeah, so you put your mouse over. You're going to see mute, a little blue box, 3 dots. Click on that, and then go to rename. And then you can type in your name.
It just says pin video for me.
Oh, it just says ping? No, just hover your mouse over it.
Yeah, hover your mouse over it. I can see it. Yeah, you hit that, and then there's an option for rename.
Yeah, do you see that?
You can also click on your actual name, the little box where it has your name, and you can rename it. Just double click.
Oh, it might be different on Windows.
Okay, let's maybe save this for after class.
Yeah, sorry.
Totally. No problem.
I'll change it briefly, and then we'll come back.
Yeah. Okay.
Okay. Good. Any other questions about anything? In terms of detail of the class or solutions or?
I do have a question on the solutions though.
Yeah.
So where was it? Hold on, I took notes. For the solution, it can only be one. It's only two. It's only the solvent and the solute, right?
You can have multiple component solutions. So you can have solutions that have more than. Usually it's just one solvent, which is the majority component, and then you could have numerous solutes. So for example, you could put sodium chloride and sugar in a solution, right? Then you'd have a sodium chloride and salt solution.
Okay.
So you can
so
have
you can have more than one.
And many times, many solutions have multiple solutes. Good question.
Okay. Thank you.
Yeah. Any other questions? Okay, let's go ahead and get going. So just refresher from last time, solution, right? A homogeneous mixture of 2 or more substances, right? Typically we call the majority component the solvent and the minority component the solute. So for example, salt water, right? Salt is the solvent. Salt is the solute and water is the solvent, right? So, and in cases like sodium chloride in water, that's called an aqueous solution because water is a solvent, and we'll focus mostly on aqueous solutions in this chapter because they tend to be the most important, okay? All right, so let's start by examining solution concentration, which you already saw a video for before coming to class today. So just remember that we can measure solution concentration in a number of different units, all right? But the main unit that we're going to be using, especially right now, is called molarity, all right? And it's moles of solute over liters of solution, okay? So you just figure out the moles of solute, divide by liters of solution, and you got molarity, which tells you how concentrated the solution is, right? The higher the molarity, the more concentrated it is, the more solute there is per unit solvent, right? So let's just look at an example here. What's the concentration of a solution containing 15.5 grams of KBr in 225 milliliters of solution, all right? And we want that concentration in molarity, right? So we're given, right, 15.5 grams of KBr, and we're also given that that's in 225 milliliters of solution. Right, and we're given the molar mass, and we're asked to find the concentration, right, in molarity, all right? So all this requires is for us to know the definition of concentration, which is moles per liter, right? So we know that the molarity is going to be equal to the number of moles of KBr divided by the liters of solution. And this is a little abbreviation for solution, okay? So notice we're given grams of KBr and we're given milliliters of solution, right? So we just have to do the conversions to the right units, moles and liters, and then divide one by the other, and that'll give us the molarity, right? So let's start with finding the number of moles of KBr. 15.5 grams of KBr, right, times 1 mole over 119.0 grams. Grams cancel, and this is equal to 0.1302 moles of KBr. We get 3 sig figs on that, all right? And then we got to convert milliliters to liters, so 225 milliliters, right, times 1 milliliter. Remember what milli equals?
1,000.
93.
Not 1,000.
1,000.
0.0.
Sorry.
Cents, yes. 10 to the minus 3, right? Liters, so we write it like that, right? Milliliters cancel, right? And that is equal to 0.225 liters, okay? So now the molarity does that block my microphone? Can you guys hear me okay?
Yes.
Raise your hand if you can hear me okay, yeah? Okay, perfect. All right, good. So molarity is then equal to 0.1302 moles, right? Divided by 0.225 liters, and that gives us 0.579. So that's how you can calculate the molarity of that solution. Does that make sense? Any questions on that? Okay, let's have you try one. You try this one. Go ahead and you try that one. Okay, try to finish up the next 10 seconds or so. Okay, looks like most of you got that. Very, very good. Let's see here, 90% of you. So that's awesome. Good job. Just really quick, in case you didn't get it, you're given the amount of sucrose and the amount of solution, right? It's a matter of, again, converting them to the right unit and then dividing one by the other, right? So for the sucrose, you have 22.5 grams times 1 mole over 342.3 grams, and that gives you 0.0657 moles, right? And for the solution, you have 35.5 milliliters, right, times 1 milliliter over 10 to the minus 3 liters, and that cancels, and you get 0.0355 liters, right? And so the molarity is equal to 0.0657 moles, this number, right, divided by the number of liters, 0.0355 liters, right? And that gives you the 1.85 molar, okay? So good job, most of you got that, thank you. Again, it's really important for you to follow along here, and when we do these polls and we do these problems, right, for you to apply what you learn. That's how you learn, right, by actually working it out, right? So make sure you're not just passively listening, you're actively involved, and you're gonna learn during these times, okay? All right, now, molarity can also be used in calculations. It can be used as a conversion factor between moles and liters, right? So notice that if you have liters of solution, and you multiply by 0.5 moles, let's say, of NaCl per liter, that converts liters to moles. You switch it the other way, it converts from moles to liters, right? So again, anytime you have something that has units on the top and the bottom, right, that can be a conversion factor between those two units, right? And you've seen that many times already. So let's just do a little practice with that here. What volume, okay, so again, we're gonna set it up given, find, right? And they're asking to find volume, so we already know we got to get liters, right? What volume of 0.255, 0.255 molar KCl solution contains 10 grams of KCl, right? So the important thing here is to realize that what this means, right? So it's best to write it out in these kinds of problems. This means 0.255 moles of KCl per liter of solution, right? And this is asking us, okay, how many liters, I'm trying to get liters, right? Liters of solution, how many liters contains 10 grams of KCl? Well, here's my conversion factor, but it's between what? Moles and liters, right? But this is given in grams, so what's the first thing I have to do?
Change it to moles.
Change it to moles, very good. So let's go ahead and do that. 10.0 grams of KCl times 1 mole over 74.55 grams, and the grams cancel, right? And then I can just now have moles of KCl, right? I can just do this all in one step if I wanted to. Divide the whole thing by, no, let me not do that. Let me just do it like this. let's just get moles first. What does that come out to be? 10 divided by 74.55 equals 0.0134. So that's equal to 0.134 moles of KCl, right? And once I have moles of KCl, then I can use this as a conversion factor, right? So it'd be 0.134 moles of KCl times, and now how am I going to write this to convert to liters?
Moles on the bottom.
Moles on the bottom, right? So 0.255 moles of KCl over 1 liter of solution, right? My moles of KCl cancel, and that gives me 0.526 liters of solution. Right? Does that make sense? See how this is acting as a conversion factor between moles and liters, right? Okay, let's have you try one. Okay, about 10 more seconds. Pardon me, Delia? All right, I'm going to end it here. Most of you got that, so that's good. Really quickly, the right answer was, of course, A, as you just saw. But the key here is to realize what this means, right? Whenever you see something like this written down, usually in a lot of calculations, you're going to need to write it in this form to use it, right? So when you see 0.25 molar NaCl, right, aha, I know that means 0.25 moles of NaCl per liter of solution, right? In this case, they're asking how many moles of solute, right, how many moles of the NaCl are present in 0.15 liters, right? So you take the 0.150 liters, and then you're going to use this as a conversion factor, right? 0.250 moles per liter. That's going to cancel, right? And that's going to give you 0.0375 moles. Okay? Does that make sense? Nayeli, do you have a question?
Yeah, I kind of solved it a slightly different way using just like the molarity formula. So it's like you're already given the moles of solute, or no, sorry, the liter.
Yeah, so you said molarity is equal to moles per liter, right? So you put in the liters and the molarity you saw for moles.
Mm-hmm.
You can do it that way. However, it'll be more convenient to do it this way, because this way you can put many of these conversions together, which we'll see we're going to be doing here very soon when we get to solution stoichiometry, right? So it'll be easier for you to just think of this as a conversion factor between moles and liters and be ready to convert back and forth that way.
Okay.
Okay?
Thank you.
But that way works. If this is all you're doing, that way works. But if you got to do more involved problems like we will in a minute, then you'll see how it's more convenient to do it like this.
Got it.
Okay. Any other questions? Okay. Let's go ahead and move on to solution dilution. So a lot of times in the lab especially, and we're not working in the lab, unfortunately, in real life this semester, but in the lab a lot of times we'll store solutions in a very concentrated form. And then when we need them, we'll use that concentrated form to make the concentration we want, right? So, you know, we may have a solution that is, you know, let's say 10.0 molar, right, that we store in the lab. And then, you know, we want to, but we only want, for whatever use, we may only want a 0.5 molar solution, right? So we'd have to take some of this solution and dilute it, right, to a lower concentration, okay? So the equation that governs that is this equation right here, solution dilution equation. If you have a solution that has some molarity and some volume, then you make a second solution, has a second molarity and a second volume, right? They're related by M1V1 is equal to M2V2, all right? And why is that? Because M1 times V1 is equal to moles and M2V2 is equal to moles. So the moles are the same in both solutions, right? It's just one is more dilute than the other, okay? So let's just do an example. So we're given that we have 0.100 liters of a 12.0 molar NaCl solution, right? And we want to have a 1.5 molar NaCl solution, right? So we want to dilute to that. All right, and we want to find what volume should we use, right? What volume, and that's going to be in units of liters, okay? So real simple, we're just going to use this equation, right? M1V1 is equal to M2V2, right? We're looking for the final volume here, right? The volume that we're going to dilute to, so we can solve this equation for V2. V2 is equal to M1V1 over M2, right? And then we just plug in. And this is one of those rare cases where you can just keep the molarity as molarity and you don't have to rewrite it as moles per liter. Again, for most calculations, you'll want to do this. For solution dilution, you don't have to, okay? So the initial molarity is 12.0 molar, right? The initial volume is 0.100 liters, right? and the molarity we're trying to get to is 1.5 molar, right? So we set it up like this. And if we multiply that out, we get our final volume, which ends up being 0.80 liters. Does that make sense? Okay, you try one. Now, this is a little tricky. I made it a little more complicated, right? So think about it carefully before you work it out. Okay, I do see we're making we're making some progress here. Some of you are doing it very well. There's a little bit of a tricky part here, right? So let me tell you what that is. So the initial concentration is 0.5 molar. That's clear. The initial volume is 45 milliliters. That's clear, right? And you have to find M2 so you can solve it for that equation. But the tricky part is, what is V2? Right? You got to think about what is V2. And notice that in this case, it says you had this much solution, and what happened? You added 25 milliliters of water, right? So V2 is going to be equal to the initial volume, right, plus the 25.0 milliliters that you added, right? So you got to read that into the equation. The way it's worded, it's telling you that, aha, the second volume is not 25 milliliters, it's 45 plus 25, right, because they were added together, right? And so that is 70.0 milliliters. Okay, so that's V2.
I have a question.
Sure.
So the volume doesn't have to be in liters. This one can be milliliters.
Great question. Let me address that. So when you solve this equation, right, we're going to solve it for M2. So M2 is going to be equal to M1 V1 over V2, right? So notice that the two volumes are one on top of the other, right? So this is going to be in molarity, and these are going to be in whatever units you want, right? Why can they be in any units you want? Because they're going to cancel one another. In other words, let's suppose I'm just going to write it. Let's suppose I write it in milliliters just to show you what happens. So I'm going to say M1 0.500 molar, right, times V1 45.00 milliliters divided by V2 70.0 milliliters, right? Now, notice what happens. The milliliters are going to cancel, right? Let's suppose I change it to liters. So if I change both of these to liters, I'd do something like this. 10 to the minus 3 liters per milliliter. But then I do the same thing on the bottom, right? 10 to the minus 3 liters per milliliter. And that, of course, would change it to liters. But notice that the 10 to minus 3's cancel. So it doesn't really matter. As long as the units are the same in the numerator and denominator, you're going to get the same answer. Does that make sense?
Yeah, that makes sense. Thank you.
You're welcome. All right. So let's see. Does anybody want a little more time on this one? Some of you are getting it, but some of you are not. Remember that the final volume has to be the sum of both of the volumes.
Yes, I need more time.
A little more time, okay. Karina, did you have another question? Or is that left over?
My hand's probably still raised.
Okay, I'll lower it. Okay, I'll lower it for you. Taylor, do you have a question?
Yeah. Is the key that it's 25 milliliters of water? Because if it said solution, would that
very
change
good.
things?
Yeah. So the key here is twofold. One is that you have 45 milliliter solution. You added the water, so it mixed. And then here we're saying assume that the volumes are additive, right? So that the final volume is the sum of those two.
Yeah, but like it's a water, so it's diluting it.
Correct.
So it has to be lower then.
Yep. Yep.
Okay.
That's right.
Cool. Okay.
That's right. Okay, I'm going to end the polling there. Show the results. The right answer is C. So more of you got C, but a few of you got A. Let's see what happened. If you put A, what did you do wrong?
We didn't add them. We just went straight forward.
Oh yeah, you probably just went.
Because I did that.
25 milliliters instead of adding them together, right? So don't forget to add them together if you got A. Okay. All right. Good. All right. Let's move on. So now we know how to deal with solution concentration, right? And we know how to convert. We know how to compute or calculate solution concentration. And we know how to use solution concentration as a conversion factor between what? Moles and liters, or liters and moles, right? Okay. So now we're going to move on to solution stoichiometry. So remember our typical stoichiometric kind of problem, right? You have A goes to 2B, let's say, right? And you're given, grams of A, and you want to find grams of B, right? Right? And do you remember what we did in order to solve these kinds of problems? We went from mass of A, right, to moles of A, to moles of B, to mass of B, right? Mass to moles to mass, right? And the reason we do that is because this conversion here, right, you got to use the balance equation to convert between moles of B and moles of A, right? And this applies to moles only, not to grams, right? So you always got to go to moles, all right? So now if you have two reactants, that are reacting in solution, right? A lot of times instead of mass, you'll be given volume and concentration, right? So if you have volume and concentration, right? In other words, if you have liters, right? And moles per liter, right? Then you can get to moles. So you can go from volume and concentration to moles of A, and then you can use the balance equation to go to moles of B, right? And then you can use the concentration again to get to volume of B, right? So it's the same idea, but instead of mass to moles to moles to mass, you're going to go from volume to moles to moles to volume, okay? But it's the same idea. You're going to use volume concentration to get to moles and then use the stoichiometry, okay? So let's do an example so you can see how this works, all right? So we're given that we have 0.150 molar KCl, and that's going to react with 0.150 liters of a 0.175 molar PbNO3 solution, right? And we're given the balanced reaction right here, yeah? And what do we have to find?
We need to find volume.
Volume, yep, we're asked to find volume, right? So in liters. So notice we're going to use this idea of volume to moles to moles to volume, okay? So from the balance equation, we can get a relationship, right, between KCl and PbNO3, right? We know that relationship is 2, in other words, the stoichiometric relationship is 2 KCl's for every 1 PbNO3, right? So there's our stoichiometric relationship that we're going to use. Where are we going to use that? Going from moles to moles, okay? So, again, the idea is we're going to go from volume to moles of PbNO3 to moles of KCl to volume of KCl, right? Solution. Does that make sense? All right, so let's do it. 0.150 liters times 0.175 moles per liter of PbNO3, right? Here, Nayeli, see, here's where it's really convenient to be able to do these kinds of calculations this way, to think of molarity as a conversion factor, right? Because then that gets you from volume to moles. Then the next part is to use this, which comes from the balance equation, right? Comes from here. And how am I going to write that? My conversion factor.
Two moles of KCl over 1 mole of the other one.
Yep. 2 moles of KCl over 1 mole of PbNO3, right? So that's going to cancel. Now I have moles of KCl. So remember, volume to moles to moles. Now I just got to go back to volume. Now I have moles of KCl, right? And what am I going to use to get to volume of KCl?
The molarity of KCl?
Yep, I'm going to use this right here, right? And how am I going to write it? Remember what this means? It means, oops, sorry, 0.150 moles of KCl per liter of solution, right?
So your moles are on bottom.
Can't see it. This means 0.150 moles of KCl per liter of solution, okay?
So to get rid of moles, you would have to have your moles in the denominator then?
Correct. So you're going to have 0.150 moles KCl, right, over 1 liter of solution. My moles of KCl cancel out, right, and I end up with liters, right? So that ends up being 0.350, 0.350 liters of KCl, right? Notice what kind of problem this is. This is kind of like, again, it's a stoichiometry problem. It's kind of like saying, how much cheese do you need to completely react with 3 pizza crusts, right? And here's my recipe for the pizzas, right? It's the same thing. How much of one of the reactants do I need to completely react with the other, right? How much cheese do I need to make 3 pizzas, right? Or actually a better analogy would be, how much cheese do I need to go with how many pizza crusts, right? With 3 pizza crusts to make the right number of pizzas according to the recipe, right? It's the same thing, right? We're just asking how much of this do you need to completely react with a certain amount of this? How much cheese to react with 3 pizza crusts? Does that make sense? I see a couple of questions. Allison.
I think maybe I got it. It's just kind of confusing to see like the molarity become moles, but I guess it's just because you're
Exactly.
with the 1 liter. Okay.
Right, but remember that whenever you see molarity, except for the instances when we just had like a solution dilution problem, almost always when you see molarity, you're going to write it like this, right? And it's going to be a conversion factor between moles and liters.
Okay.
Okay? So whenever you see molarity, it'll really help you to write it like that.
Okay. Thank you.
All right, let's see. Delia.
So are you allowed to start off with the molarity? Like, you know how you started with liters? Are you allowed to start off with molarity if you wanted to?
You could, but it just doesn't, conceptually, it doesn't make a lot of sense, right? But you can. In other words, I could have switched these two without much of a problem, right? But it just conceptually, I think it makes more sense. I start with liters. I use the molarity to convert to moles, right? It'd be sort of like saying, you know, if I was going to convert centimeters to inches, would I start with centimeters or would I start with the conversion factor between centimeters and inches?
Okay, yeah, that makes sense.
Right, you could start with the conversion factor, but it just doesn't make as much logical sense as starting out with centimeters and then using the conversion factor to get to inches.
Okay, thank you.
Yeah, yeah, you're very welcome. Let's see, any more questions? Okay, you ready to try one? Here's one for you. Most of you are working these out. I see a few of you that I don't know if you're trying to work it out or if you're just not getting to the answer, but I really encourage you, all of you, to use your time efficiently, right? How to use your time efficiently? You gotta engage, you gotta remember the recall effect, right? You don't learn just by listening to me, right? You can't learn just by listening to me. You actually have to do it, right? So that's why I do these polls. That's why that's why during all lectures, I want you to be involved, right? I want you to be applying what you're learning. I want you to be recalling it and applying it because that's how you learn, right? So make sure you're not just sitting there listening to me. Make sure you're joining in. Get a piece of paper and a pencil out and work this one out. Come on. Okay, about 10 more seconds here. Okay, I'm going to end it there and show results. And the right answer is D, which most of you got. A few of you were thrown off a little bit here. So let me just show you what's going on here. You got 0.2 molar of A. You got 0.5 liters of 0.1 molar B, right? And you got to remember, whenever you see these molarities, right, to write them out that way, right? So this means 0.1 moles B per liter. And what does this mean? 0.200 moles of A per liter, right? Those are your conversion factors to get from moles to liters, right? And then here's your conversion factor to get from moles of one thing to the moles of the other, right? So you're going to start out with 0.500 liters of B, right, times 0.100 moles per liter. That's going to give you moles of B, right? And then you're going to use the stoichiometric relationship. How are you going to write it?
1 mole of A over 2 moles of B.
Correct. 1 mole of A over 2 moles of B. Now it's going to cancel B. Now I got moles of A. Now I can use this to get liters of A, right? 0.200 moles of A per liter. And that's going to cancel. And that's going to give me my 0.125 liters of solution A. You see that? Liters to moles to moles to liters, right? Very similar to our stoichiometry of mass to moles to moles to mass, right? It's the same exact problem. It's just now we got molarity and concentration, liters and concentration instead of grams to moles. Questions? Is that making sense? Okay, very good. Very good. You guys are doing great. I appreciate it. Okay, let's see. Let's move on to types of solutions. So not all solutions are created equal. There are different types, so let's dive into that a little bit. First of all, how does a solution form? And so let me just give you a simplified picture first. Imagine you have water, right? So water is made up of lots of little water molecules, right? More than you can imagine. And now you're going to take some substance, which is made up of its own molecules, right? And you're going to put that in there, right? So this is your solvent, this is your solute, right? And now there's going to be a sort of competition of forces, and we really haven't talked about what are called intermolecular forces yet, but all particles, like water particles, or the particles that compose a solute, such as sugar, for example, the molecules are attracted to each other, right? Water stays together as a liquid because the water molecules are attracted to one another, right? Sugar stays together as solid sugar. Why? Because the sugar molecules are attracted to one another. They kind of stick together, kind of like, have you ever seen those little magnetic marbles that you can buy like at science stores, right? And the magnetic marbles kind of all stick together, right? You can kind of think of water, right? Water molecules as the marbles, right? And they sort of are attracted to one another, right? And so that causes them to stick together, to stay together as liquid water, all right? Similar thing happens in sugar. The sugar molecules are kind of like those magnetic marbles, and they are attracted to one another, and that causes the sugar to stick together as solid sugar, right? So you can imagine what happens when you put the sugar into the water. all of a sudden there's a competition between these forces, right? These particles have their attractions to one another. These particles have their attractions to one another, right? But when you put them together, now you have new attractions, right? It's kind of like, you know, high school kids going to college, and all of a sudden there's new attractions between the new mixtures of kids, right? And so the question is, which of those attractions wins, right? Do the sugar molecules prefer each other, right? Or are they attracted more strongly to the water molecules? If they prefer each other, then the substance does not dissolve. If they prefer the water molecules, then the substance dissolves, okay? So, so that's kind of the way we think about solubility. So let's think of two different kinds of solutes, all right? First, a molecular solute, like sugar, all right? So here's the sugar, here are the sugar molecules, all right, all attracted to one another. And here are the solvent molecules, let's say water, right? And so you have these attractions and you have these attractions, right? In an ionic solute, such as sodium chloride, just a little bit more complicated because the sodium chloride itself has two different types of ions that make it up, right? You have a positive ion and a negative ion. So sodium chloride is held together, of course, by these attractions between positive and negative, yeah? So what happens when you put it into water, the sodium ions are attracted to the negative part of the water molecule because water molecules have actually a negative part and a positive part for reasons we'll get to later in this course, all right? And so the positive sodium ions are attracted to the negative part of the water, and the negative chloride ions are attracted to the positive part of the water molecule, right? The negative chloride is attracted to the positive. So those are the interactions that occur, all right? Why does water act this way? Because the electrons in water are not evenly distributed, right? Water is what we call a polar substance. And if you look at this, this is kind of like a map of where the electrons are in the water molecule, and they're concentrated over here. So this area tends to be electron rich over by the oxygen, and out here between the hydrogens tends to be electron poor. So this tends to be more negatively charged, this tends to be more positively charged within this water molecule, all right? So what happens? In NaCl, if you put NaCl into water, all right, you have the attractions between the ions, right, that hold NaCl together. But then you have the attractions between the water molecules and the ions. So slowly, and maybe not so slowly, but you can see it, you can actually see this happen when you put sodium chloride in water. You have to stir it a little bit. And during that stirring process, what's happening is the water molecules are coming up and grabbing these ions, right? And you have strong interactions then between the positive ion and the negative side of the water molecule, and the negative chloride ion and the positive side of the water molecule, right? And that causes the thing to dissolve, yeah? In sugar, you have a similar process, except in sugar, you don't have positive and negative ions. Remember, because sodium chloride is what kind of a compound?
Ionic.
Ionic, right? Metal and non-metal. Sugar, on the other hand, is an organic molecular compound, all right? And you don't have these two ions. So in sugar, the water molecules are attracted to the sugar, and they basically pull them apart from one another, right? And the sugar molecules get solidated in that way. So we say that ionic compounds like sodium chloride dissociate into their ions when they dissolve, okay? But molecular compounds like sugar, they dissolve as molecules, all right? They don't get torn apart the way an ionic compound gets torn apart into its individual ions, all right? So that turns out to be very important. When you have a sodium chloride solution, you don't have any sodium chloride units in that solution, right? Instead, you have sodium plus and Cl minus dissolved in the water, okay? We call that an electrolyte. So an electrolyte is a substance that will that will form a solution that conducts electricity. Okay, so it turns out that in order for a solution to conduct electricity, it needs these dissolved ions, because those are the things that carry the current, the electrical current. Nayeli, did you have a question?
Yeah, I was gonna ask you whether the structure of the water molecule affects like its polarity.
Yes, absolutely right. If it was not structured this way, it would not be polar, which is
Right.
crazy to think about.
Okay.
Yeah. So it absolutely affects it. It's crazy.
Yeah, because I remember that the water molecule is bent, so I'm kind of like curious as to, is that why it is polar, because it is bent?
Yes, exactly right. It's polar because it's bent, and if it wasn't bent, it wouldn't be polar.
Okay.
Yeah, and we'll get to bonding models and ways to figure out the shape of molecules that will then allow you to predict whether molecules will be polar or not. So we'll get to all that, Nayeli, and you'll be able to understand why water is polar. Okay? Any other questions before I move on? Okay. Electrolyte substance that will form a solution that conducts electricity. Sodium chloride is an example of a strong electrolyte. And a strong electrolyte is a substance that completely dissociates into its ions. Sorry, I'll just say, yeah, a substance that completely dissociates into its ions in solution, right? So we see that sodium chloride completely dissociates. Contrast that with sucrose, right? Sucrose is C12H22O11. It's this bigger, more complicated molecule, but it does not dissociate, right? It's a non-electrolyte. So electrolyte, strong electrolyte, non-electrolyte. Substance that forms a solution that does not conduct electricity, right? So a sugar solution would be an example of a non-electrolyte solution. Sugar is a non-electrolyte, okay? So let's look at the difference. If I had a salt solution and I formed a little circuit with a battery, right? And a light bulb in line with the circuit, right? If I have a sugar solution, electricity will conduct from this electrode to that electrode, right? And the light bulb will glow. Why? Because the solution conducts electricity. Why? Because salt is a strong electrolyte, yeah? On the other hand, if I have a sugar solution, right, put sugar in here, have the same setup, the light bulb would not glow, right, because electricity cannot be conducted from here to here. Now, this would have to be pure water with added sugar and nothing else added, right, because is our water that we get out of our taps, for example, is that pure water?
No, it has chlorine in it, doesn't it?
Has chlorine and it has a lot of dissolved ions, right? We have pretty hard water in Santa Barbara. It has things like calcium and magnesium and other ions dissolved in the water. So the water out of your sink is not pure water. You'd have to get deionized water, right, in order for it to be pure, okay? Megan.
Is it possible to have a weak electrolyte
Yes.
where like some of them dissolve but not all of them?
Yes, we're getting right to that right now. We're almost there. So a weak electrolyte is a substance that partially ionizes in solution. And most weak electrolytes are weak acids. So let me just define acids real quick. Acid, substance that ionizes into H plus, size it upsize into H plus and it's wrong. Substance that ionizes to produce H plus in solution. Okay. So, for example, HCl is an example of an acid. You put it in solution, it ionizes and forms H plus Cl minus. Notice that it's kind of weird, right? Because normally substances that do this, we think of them as ionic compounds, right? So something like NaCl, right? Like we just talked about. But acids do the same thing, all right? But acids can be strong or they can be weak. So for example, HCl is an example of a strong acid. So it completely ionizes. An example would be HCl. Okay, but we could also have weak acids. They only partially ionize. And we symbolize that with a double arrow. And so for an example of a weak acid would be something like acetic acid. Acetic acid is the acid in vinegar, right? So if you have a jar of vinegar, that's essentially an acetic acid solution, all right? And acetic acid is an example of a weak acid, H plus C2H3O2 minus, right? We symbolize that with the double arrow, like this. This is an equilibrium arrow. We'll talk more about those later on in this course. But the double arrow signifies that it does not completely ionize. So what do I mean by that? I mean, if I had a solution of acetic acid, it would look like this. And this is subtle to look at, but this is a molecule of acetic acid right here. So this, notice is OH. This is C2H3O2 with the H on it, okay? So that's the unionized form right here. Here's an example of the ionized form. It's lost one of its hydrogen atoms, right? But notice what this solution has. It has mostly unionized acetic acid, and here's one molecule that has ionized. Well, I guess there's two. There's this one, and where's the other one? This one. Yeah, this one's ionized, and this one's ionized, okay? So in the solution of acetic acid, you have some that are ionized and some that are not, all right? That's known as a weak acid, and that solution then is known as a weak electrolyte. All right, so here we go. Non-electrolyte does not ionize at all, right? Sugar is an example of a non-electrolyte. Strong electrolyte completely ionizes. Most ionic compounds are strong electrolytes. Okay? A weak electrolyte only partially ionizes. The main weak electrolytes that we'll be working with are weak acids. Okay? Strong acids are, of course, strong electrolytes. Okay? So you can sort of think about it this way. You have electrolytes, right? Electrolytes can be strong, they can be weak, or they can be acids, right? And then acids themselves can either be strong or weak. A strong acid, of course, is a strong electrolyte. A weak acid is a weak electrolyte. All right? And then you have non-electrolytes. Okay? And those are going to be molecular. Right? These are going to be ionic. All right, so those are the different types of solutions. All right, so really just if you have these three categories in your head, strong, weak, non, right? And then you realize that, okay, most weak electrolytes are going to be weak acids. That'll be good. All right, does that make sense? Questions? Okay, let's see. We're getting close to the end here. Let me just introduce this last topic, just so we have it kind of under our belt for next time, and we'll start with this topic next time. I see there's a quick question though, Taylor.
So just to clarify, a strong electrolyte is basically completely dissolves or completely
dissociates.
Yeah. And then a weak is anything between a strong and a non-electrolyte.
Correct.
Okay.
Correct.
Okay.
Yep.
So it's not like a value, it's just anything in between.
Right.
Okay. Cool.
I mean, in reality, it is kind of a continuum, but it's helpful to categorize in this way. And for our purposes, we can just categorize them as strong. We can think of strong as completely ionized. Weak is just actually just a little bit ionized, and then non-electrolyte is non-ionized.
Okay, cool. All right. Thank you.
Yeah. All right. So the next question then is solubility. You know that you put some things in the water, like let's say sodium chloride, and it dissolves, right? You also know that you put other things in the water, like let's say sand, and it doesn't dissolve, right? So some things are soluble, some things are not, right? It ultimately comes back to this sort of competition between forces, right? If these forces, the ones that hold the solute together, are stronger than these forces, then guess what happens? Does this substance dissolve or not? If this is stronger than this, will this dissolve in this or not?
No.
No, right? Because these guys are going to win. These guys are holding each other more tightly, right? This couple came as, this is a couple that sticks with their high school sweetheart, right? And doesn't fall for the new people at college, right? However, if this attraction is stronger than this attraction, then it does dissolve, right? In that case, you know, the college attraction is greater than the high school attraction, so you get a solution, yeah? Okay? That's my analogy here for whether something dissolves or not. Now, it turns out that predicting that, well, you can imagine, predicting it in people is pretty hard, and it's pretty hard to predict it in solutions as well, all right? You can't just look at a substance and say, aha, this substance is going to be soluble and this substance is not going to be soluble, right? It just doesn't, just hard to predict, all right? But if a substance is insoluble, that means that it won't dissolve in solution. Does not dissolve. And if it's soluble, that means it will dissolve. Or it does dissolve, sorry, I must say it does. Right? So, some substances, like for example, silver nitrate, is soluble. You put silver nitrate in solution, it's a ionic compound, all right? And it breaks up, it dissolves into its ions, all right? And it forms Ag plus and NO3 minus. Whenever an ionic solution dissolves, right, it always forms a strong electrolyte. It always dissociates into its ions, all right? But if you put silver chloride in solution, turns out it doesn't dissolve, right? If you put silver chloride or white powder in a solution, it would look like this, right? It's insoluble. It just goes down in the bottom and sits there, okay? It doesn't dissolve. So we say that silver nitrate is soluble, but silver chloride is insoluble, right? So how do we know whether one substance is going to be soluble, or how do we know whether a substance is going to be soluble or not? Well, again, it's very difficult to predict, but luckily we have some experimental observations that can help us to predict that, okay? And that's where we'll start next time, is with these solubility rules that help us to predict whether a particular substance will be soluble or not, okay? We'll start with that next time. So we're done with the topics for today. I will stick around and answer any and all questions. Davis, I see your hand up. I'll wait till I'll dismiss class and end the recording, and then I'll answer your question, okay? Thank you, everyone, for your attention.
Thank you.
I appreciate it. Thank you for those of you that turn on your cameras. I really appreciate that. Thank you for those of you that are working along. It's fun because those of you that turn on your cameras, like, it's the same group, and I feel like I'm getting to know you a little bit, even though I'm not getting to know you personally. I'm getting to know you on Zoom. Someday I'll see you out in the streets of Santa Barbara, and we can say hi to each other, I hope. Yeah, I'm sure it will happen. So anyway, thank you, everyone. Have a great day, great weekend, and we'll see you next week. Bye.
Yeah. Bye.